Okay, so good morning, good evening, everyone. So it's my pleasure to chair this session. So my name is Ren Baoliu from the Chinese University of Hong Kong. So in this session, we're going to have two speakers. The first speaker is Professor Sophia Economou from Virginia Tech. She is the William Heisinger Junior Senior Faculty Fellow in physics. Okay, so Sophia, are you ready to
Yes.
present? Great. Hi.
Thank you, Remba, and thank you to the organizers for the invitation. So today I'll talk a little bit about the work of my group on spin-photon interfaces focused on quantum repeater network applications. So I'll be talking about basically two directions under this kind of umbrella of research. Both focus on spin-photon interfaces and both focus on repeater networks as an application. The first one is based on the memory-based scheme, where we'll discuss high-fidelity entangling gates in the MV center between the MV center and the nuclear spins. And the second is all photonic repeaters, and particularly protocols for deterministic generation of graph states from controlled and pumped emitters. So since this is a very focused conference, I don't need a lengthy introduction, but just to remind you, the objective of quantum repeaters is to allow two parties that are separated by long distance to share entanglement. And because of photon attenuation, this cannot be done without doing something in between to enhance the quantum state. So the fact that photons are absorbed and lost means that we cannot just use a single fiber all the way from Alice to Bob. We need to do something in between. And the canonical approach to quantum repeaters is to have at these intermediate nodes quantum memories, which emit photons that are entangled with them and which can then be entangled with each other at the node. And this way, through entanglement swapping, entanglement spread out further from where this measurement is happening and eventually all the way to Alice and Bob. It's a very nice experiment, well-known experiment from about 5 years ago, demonstrated the creation of entanglement over more than a kilometer distance between two NV centers in diamond. And I will be focusing at least for the first part of the talk on that approach, where the NV centers are used at each node. And the electronic spin of the NV center is the active spin-photon interface, and then there's nuclear spins, which can be used as local memories. So kind of an overview of the scheme. The NV center can emit a photon, which is entangled with a spin, and then that photon is sent to a node at some distance away, in this case on the order of a kilometer. And then the same thing can happen from a different NV center, which is located in somewhere far from that. Because this photon emission process is probabilistic, not fundamentally probabilistic for emitters, but this system just happens to have a low emission rate into the desired mode. This process can be repeated until there's the photons are emitted and measured here. Another probabilistic element, which is fundamental, is the Bell measurement itself. So at this node here, the two photons arrive, and the Bell measurement, even though both photons made it here, might fail. So this process can be repeated until entanglement is established. And once that happens, then information is sent back to the emitted node, and the state, and now the state is an entangled state between the two NV centers, electronic spins, but now you want to reuse these emitters. So you swap out the state through some series of C0 gates or swap gate, and you swap it out to a nuclear spin. And you do the same here. So then there's entanglement between two nuclear spins in two diamonds that are located at different locations. And then the MV center emitter is now free to emit another photon and repeat the protocol, let's say with a different node, and spread out the entanglement that way. So this is kind of an overview of the scheme. And the part that I'll be focusing on for this talk is this part where you're swapping out the state, or where you're trying to entangle the MV center with a nuclear spin. And there's been a lot of work over the last 10 to 15 years where people have controlled the nuclear spin of a C13 atom located somewhere nearby the MV center. So I'll be mostly focusing on the work, the approach that the Delft group has taken, which is a dynamical decoupling approach, and I'll talk about that more. So there's a 1% natural abundance of carbon in these lattices. And for now, let's only consider one nuclear spin coupled to the MV center. And we're only considering also the two spin states out of the 3 of the ground level of the MV. In that case, the Hamiltonian can be brought in a form that looks like this, where there's a projector on the electronic spin tensored with a Zeeman term on the nuclear spin, and then another term that now the electron is in the 1 state, and the nuclear spin can see the electron. So the Zeeman term is actually modified by the hyperfine interaction, which has 2 parameters, a perpendicular and a vertical. So because of the form of this Hamiltonian, the evolution operator that the overall evolution operator of the 2 systems inherits this form. There's a projector on the electronic spin, tensor with some evolution on the nuclear spin, and similarly for the other state. And in terms of the goal of creating an entangling gate between the 2 systems, what we would like is for U0 and U1, which are, of course, rotations on the Bloch sphere of the nuclear spin, to be as different as possible. So if we have a rotation about pi-half, about the x-axis by pi-half for one of these evolution operators, and the other one being a rotation about pi-half about the minus x-axis, then these net evolution is the same as a C0 gate. So one challenge is that, of course, you don't really have only 2 systems. You have the MV center coupled simultaneously to a larger number of nuclear spins, and these interactions are always on. So this idealized form of the Hamiltonian evolution operator is actually not, not what happens in reality. So to control multiple nuclear spins, the approach that the Delft group is taking, shown here in other publications, is to use a dynamical decoupling sequence, specifically CPMG, where the pulses are all equispaced other than the first and the last. And by using this dynamical decoupling sequence, the idea is that generically you decouple the electronic from the nuclear spin, but for specific nuclear spins that are based on resonance conditions, so for times, interpulsed times shown here, then the coupling is actually amplified. So this is a way to select one nuclear spin out of the many that are coupled to the electronic spin. Of course, it can't be too many, because then you start hitting multiple resonances at the same time. So if you look at what the evolution operator looks like, you can plot for the U0 and U1. There's an axis of rotation for each, and you can look at the dot product. So since you want your U0 and U1 to be as different as possible, you want this dot product to be as close to -1 as possible. And at the same time, you want some non-zero phase, which or rotation angle, which you can then repeat the sequence over and over until this rotation angle becomes what you want by adding up little segments of this. So this way you can create C0 gates, and they have done this experimentally successfully. And achieving interaction, gates with nuclei that are coupled more weakly than the time scale given by T2 star. Now, if you zoom in to the angle plot here, you see that this angle is very small. So we can think of this modulo 2 pi, but it's actually not kind of infinitesimally small. So one challenge here is that if I want to achieve a C0, I actually need to repeat the sequence many times. So I'm multiplying this delta phi over here. And that means that I cannot achieve go arbitrarily close to 2 pi, which is my goal. I'm sorry, 2 pi, which is my goal for C naught. But instead, I might under or overshoot it. So there's a granularity in this angle phi coming from the fact that I have these kind of finite steps every time I use the CPMG sequence. So there's more complex sequences, including the Urich dynamical decoupling sequence, which is very different from the CPMG in the sense that it's not equispaced. So there's a distance between the pulses that depends on which number pulse you're looking at, which is shown here. And this was first put forward by Ulrich, and then a lot of work has been done by our chair, Rambalu, on these sequences. So what we looked at is controlling multiple nuclear spins using Ulrich sequences, which is a little bit more complicated than the CPMG because there's less, these are a little bit more complex. So we plotted the same thing, essentially. We looked at how does the inner product of the two axes of rotation look like, and the phase, the angle for, we kept it to UDD4 here, but we also have higher orders. And we were able to also get some approximate analytical expressions. If you zoom in now into the angle of rotation, which is the issue I raised in the previous slide, you see that while CPMG is very far away from 2 pi, Urich comes quite close. So that means that I can take smaller steps, which I can add up to go closer to 2 pi if I do a lot of UDD4s. So I don't need to do these UDDNs, which would result into pulses are too closely spaced to each other. I can just take the UDD4 unit and repeat it. However, this would still be an issue because since now I have very small steps, I need to add a lot of them. So that could make the sequence be too long. So what we did is we actually consider hybrid sequences. So the idea is I use CPMG up to a point where I can get very close to the pi C naught that is my target. And then I use a few UDD4s just to supplement and reach C naught. And we see that this performs much better than just doing CPMG because it does precisely what it set out to do. It addresses this issue of granularity. So if you look at the CPMG, this is infidelity is a function of the two hyperfine parameters. You see that it has this structure here with regimes of lower fidelity, whereas the hybrid sequence is much smoother because that's what it does by construction. It achieves higher fidelity without actually sacrificing too much of the gate speed. And the reason is that this looks very much like CPMG, only that there's a small addition of UDD. In other respects, these hybrid sequences look very much like CPMG because they kind of inherit a lot of their decoupling power from CPMG. But then UDD, if we were to use UDD alone, we would pay the price of longer sequences, but actually we would be able to have better decoupling power and selectivity. Of course, at the expense of slower gates. So there's flexibility depending on what one wants to achieve. All right, so just to go back and review the protocol, the part I talked to you about is this piece here where I need entangling gates to achieve swap operations and also measurement of the nuclear spins. One issue with this protocol, not only for MV centers and not only for color centers, in general for the memory-based schemes, is that classical information needs to be sent back to the node. So when this Bell measurement succeeds, you need to inform here this node that, okay, now you can swap out the state. So to address that and other issues that come about with memory-based repeaters, Zuma and collaborators put out this idea several years ago now, where they proposed all photonic quantum repeaters. So in this scheme, you get rid of the quantum memory altogether, at least in principle. And the idea is that you generate these highly entangled photonic states called graph states shown over here in one node. And then you send half the photons in a neighboring node and half of them in the other neighboring node. And there's Bell measurements happening at these intermediate nodes. So these graph states are well known in the context of measurement-based quantum computing. They were introduced in the seminal paper by Rausendorf and Briegel, where it was shown that the cluster state, a two-dimensional cluster state shown here, this is a small version of one, but ideally you imagine this extending to as many qubits and as deep a cluster as you need to run a quantum algorithm. They showed that if you have access to such a state, you have essentially created all the entanglement you need up front, and then quantum computation proceeds with single qubit measurements. So states like these, what they represent is every circle here is a qubit in state plus, and every line is a CZ gate. And then similarly, the same rule applies here. So this is the repeater graph state from the paper I showed you in the previous slide, where there's these core photons over here, which are all-to-all connected, and there's these arm photons sticking out. And these arm photons are what is used for the Bell measurement, and I'll show you how in a moment. Another useful element here is that these states can be described in terms of stabilizer formalism, where you have a set of stabilizers that you can use to describe the state instead of writing down a wave function following this recipe, which of course would be inefficient for more than 3 or 4 qubits. So the graph states have some very nice properties that allow you to both exploit for quantum computing, but also for the repeater schemes that I'll talk about. So the way they perform under measurement is the following. If I make a measurement along the z-axis, then I'm removing a qubit, the qubit I measured, but I'm leaving the graph structure of the remaining graph intact. If I make a y measurement, then I'm removing the edges from the neighbors of the qubit I measured, but I'm also creating an edge if there weren't any already. And then the x measurement is more complicated, but actually 2x measurements in adjacent qubits have a nicer way of being described, which is what we need here. So if I measure 2 neighboring qubits both in x, then of course I'm removing them, but I'm also connecting all their neighbors to each other. So here each has one neighbor, and I create a straight line. And this is a property that is used in this protocol, as I'll talk about in a moment. So what we're concerned about is, given these nice properties that these graphs have, how do I actually create them? And of course, one way you can create them is through linear optics and post-selection. So you can send in Bell pairs through optical elements and make a measurement, and upon they click on a detector, which is a probabilistic event, you can kind of glue together clusters and create larger clusters. This is a challenging thing to do. There's been really nice work from Jiawei Pan's group in China, where they have entangled on the order of 10 photons. But still here, every time you kind of do this, you have to pay the price of a 50% probability for a Bell measurement. So we want to go back and think about, in principle, deterministic generation. So you can look at a lambda system. And you know that for a lambda system, if you have the right selection rules, you can get spin-photon entanglement. This is not enough. But however, if you modify your level structure slightly, then you can put your system in a superposition of the ground states and excite it in a superposition of the excited states, and then let it decay. And the first step is the same as having a lambda system. However, if I were to repeat this protocol, keep pumping, then I would be able to get a GHZ state shown here, which is equivalent to a star graph up to single qubit gates. This is still not quite what we need, but it's already a useful tool. Then if I add one more capability to my system, which is allowing to do gates between the 2 ground states, then if I add a Hadamard after every pumping event, and then I repump, it was shown by Linder and Rudolph that you can actually get a 1D cluster state. So this now starts becoming very useful, because I can generate strands, different strands and types of graphs from emitters, which is in principle deterministic. I want to say to kind of stress that this is in principle, meaning that there's no fundamental physical reason that I could not extract all the photons, at least in principle. There's also been some nice experiments by Gershoni's group, where they used the quantum dot and they showed you can extract a 5-photon linear cluster state. And very recently, actually a paper that was just published from Eichler and Wallraff at ETH showed that you can do the same thing by manipulating transmons and emitting microwave photons. So it's a very exciting field, and my group is very interested in it. So our contribution was to go beyond one-dimensional cluster states and realizing that if you create entanglement between emitters, then you can transfer that entanglement to the emitted photons, which means that you can actually create structures, graph structures, much larger than one-dimensional. In the work we did with Terry Rudolph and Mercedes, who are now in PsiQuantum, we showed that you can actually, if you do a CZ between emitters and then you do the Rudolph-Linder protocol for each emitter, and then you add a CZ at every step, you can get a 2x(n) dimensional graph. And then the question I want to address here is, how do I get the deterministic generation of a repeater state, which is actually what we want. So this looks quite different than 2x(n). And I'll show you now how you can get it quite simply with only one emitter and one ancilla. So the first step is I do a CZ gate between the emitter and the ancilla, and then I pump the emitter, which is the red dot, the red circle. That way I generate photons, I pump it twice, which are now anchored between the ancilla and the emitter, and then I measure the emitter. By doing this, I leave the strand anchored to the ancilla, and then I re-entangle them with another CZ gate and I repump. So that way I create another arm here, and I can just keep going to create as many arms as I need. And then using these magic properties of graph states under measurements, by doing a Y measurement here, I actually create these connections among all the neighbors of the ancilla that I measure. So this is a way to create a graph deterministically, at least in principle, so long as you catch all the photons, from very, very small resources. All you need is one emitter and one ancilla, and the ability to create an entangling gate between them. Now, if we go back and we revisit how these perform in a network, we have to remember that you need the Bell measurement in the intermediate node to be successful. So here I'm assuming this Bell measurement has already succeeded, and I'm assuming these have failed. And once this happens, now I use the properties of graph states under measurement. So what we do is we go and we measure these in the z direction so that we get rid of them from the graph. And then we measure these photons in the x basis. And if you remember 2x neighboring x measurement, just remove those qubits and connect the neighbors. And that's how this is achieved. However, if I start looking into what's the probability that I do create a connection using this repeater graph state scheme, you have to have at least one Bell measurement succeed at each node, at a given node, and then all the z measurements have to succeed, and all the x measurements, and the x measurements have to succeed here. So this means that if I were to calculate the probability that I establish a connection at a node, this is bounded by the probability that the x and the z measurements succeed, which means that these photons have to make it there. So that means that anything I gain by having this redundancy in doing the Bell measurements is actually hampered by the fact that I need all the photons to arrive. And if I need all the photons to arrive, it means that that would not be able to beat just one photon arriving, which would be the very naive thing of sending a Bell pair. So to deal with this, the inner photons have to be redundantly encoded. And I'm not going to go into too many details, but basically the idea is to use a protocol put forward by Terry Rudolph and his then student, Mike Varnava, where you redundantly code one photon into these tree-like structures shown here. And if you do that, and you use the fact that we know what the outcome of a stabilizer measurement should be, then if you lose one photon here, you know that, for example, ZXZ measurement should give you 1. If I were to lose this photon and I was measuring Z and X here, then I can infer the value of the photon I lost based on this outcome. So if it's -1, I know this would be -1, and vice versa. If it was 1, it should be 1. So this is a nice way to protect against photon loss, and it's what's built into this idea of repeater, all-photonic repeater. So in reality, the state you want to create doesn't look like the left-hand side, actually it looks like the right-hand side. where now the redundantly encoded photon is shown in here inside this region. And you see it looks quite complicated. So it's actually not obvious. How can I create this? Because this one, it was actually, okay, you can argue this was intuitive the way I showed you. We can create it using an emitter and an ancilla. But now how would I create such complex states as the one shown here? And actually we can do this, we can do this without increasing the resources too much. So here, let's consider 4 matter qubits. I'm considering all of them but one to be emitters. And now what we can do is we can pump the one emitter in a way that I create these graph structure here. So the blue dots are the photons, the purple are the emitters. Then I can do a CZ gate between the emitter I just used and a neighbor. And now I can pump one more photon, and I can create a little piece here of this tree structure. Now I measure away the emitter that emitted this tree structure, and I could repeat this process. So then I can create, so this is the analog of creating 2 arms in the earlier approach I showed you. So I can get this. And now I can do a CZ gate with a difference between this one that carries all the photons, so to speak, and another neighbor. And now I can increase the depth of this tree by 1 by pumping, again, now the second emitter. And if I keep going, then I can get deeper and deeper trees, as shown here. And this tree is anchored to this third emitter shown here. So if I just use this orange dot to denote this redundantly encoded state, then it kind of looks like this. So the very last step I need is to do an entangling gate between an emitter and that qubit, and the emitter and another qubit. So this last one is the one I haven't used yet. And now by using the property that 2x measurements of neighboring qubits allow me to connect all their neighbors to each other, gives us a structure like this. So you see that I get exactly what I want, still from very few resources compared to other schemes. And actually there was a work by Englund and Guha where they showed that to beat the direct transmission, you need on the order of 1 million single photon sources per node. So we wanted to see how well does our protocol work. So we compared to repeaterless transmission, where we just compared to sending bell pairs. And we looked at what rate can you achieve per matter qubit. And this is the rate optimized over distances for different distances. And you see that there's a large region where you beat repeaterless transmission. And then we also compared to quantum memory-based schemes. And we found that for physically reasonable parameters, you can actually beat the quantum memory-based scheme. But this work is actually the first step we took, and we didn't take too many details into account. It was a very conservative estimate where the only handicap of memory-based approach was communication back to the node. And we used the rate per matter qubit as a performance metric. All right, so the very final point I want to make before I conclude is that we can achieve this with the systems like MV centers, where we have an emitter in the MV electronic spin electron interface. And then we have nuclear spins as the memories, which can be used as ancilla. And then there's more nuclear spins which can be used for encoding. So that takes me to my summary. So the first part of the talk focused on memory-based repeaters, and specifically how to implement the entangling gate between the emitter and a nearby memory. And then the second part focused on generating these repeater graph states from few resources, especially emitters and the ancilla that are coupled to them. So that brings me to the conclusion, and thank you.
Yes, thank you, Sophia. So I think you have used all the times that we have for talk. So maybe, I don't know, like we can have, I have just very short question, okay? So, so what would be the effects of the interactions between the nuclear spins when you consider this, control gates over multiple spins?
Sorry, could you repeat the question?
Yeah, in the quantum gates on the nuclear spins,
Yes.
So
You're asking what's the effect of the other nuclear spins?
yeah, the interaction between the nuclear spins. So.
Oh, I see. Yes. So that we have omitted, but the time scale is such that those should not be too important. We have taken into account, though, interaction of nuclear spins with the emitter during the protocol, and those, so long as you don't have a very big bath, are actually not a problem.
Okay, so I think we're not going to have time for more questions. Yeah, thank you very much. And okay, so you can hear the call right here. Okay.